Hi there, guys. So I'm going to prove Euler's formula in this video here, and we're basically talking about our complex numbers written either in Euler's form, so we would have r e to the I theta, or also r cis theta, which would be our polar form there. And so these two things are equivalent. This cis theta here is essentially this thing here, and r is, of course, on the Argand diagram, it's the length of your complex number. So there's r, and theta is the argument of your complex number. It's measured from anti-clockwise from the real axis on the Argand diagram. Okay, there's z in this case. So this is just equal to z here. And what we're going to try and prove is just this part. So we don't need the r and the r there. Obviously, if we times both sides by r, then you obviously get the same, you get the result that we need. Okay, so a lot of books skip over this. That's why I'm giving this proof separately here. And also, I've just taken this one from a choice of proofs here. And so there's proofs from, if you put in here, let's go, what is this? This one is called Euler's formula. And if we have a look at the proofs here, I've chosen the second of the proofs here. So I'm just really working through the second proof here. Okay, so here we go. So little proof, let's just find this thing here, say that what we're doing. And we're going to say, to start off with, let e to the ix rather than e to the I theta equal to r cos theta plus I sine theta. I'm going to put that in brackets. It's already factorized out my r there, and this is, if you like, your cis theta. Same thing. Okay, so deliberately I haven't put an r on the front here. So I'm going to show what r is equal to in this situation. Hopefully r is going to be equal to 1. And I'm also going to, I've not got theta here, which you can see here as well. And again, hopefully I'm going to prove that x is equal to theta in this question. Okay, so the way in which we're going to do this is differentiate both sides with respect to x. So if I differentiate this side with respect to x, that's just using your exponential laws with differentiation. So using the chain rule essentially, and obviously e to the x differentiating to be e to the x. If you've got a constant in front of here, then the chain rule says that we need to put a constant in front there as well, times by the derivative of u, if you like, our function inside the function. Okay, so this one is going to give us I e to the I x under differentiation. And just to show what we're doing on the other side, we're saying d dx of this thing on the right-hand side, which is r. And then let's just type in cis theta for brevity there. So we've got essentially two functions inside here. We have r, which is potentially dependent on x, and we've got cis theta, which is also potentially dependent on x. Now, presumably, some of this on this side is going to be dependent on x, because this is dependent on x, and that's how we set the whole thing up. So we're going to assume that this and this are two functions which are dependent on x, and we're going to differentiate with respect to x. Okay, so essentially what we're doing here is differentiating a uv. So we're going to use the product rule for differentiation here, and that becomes uv dash plus u dash v. Okay, now if you're not sure where this is coming from, then you need to go back to the product rule for differentiation, because that would have come earlier in whatever course you do. Okay, so now we're going to differentiate this thing here, and so we've got u is equal to r, and r is some function of x, so we could say r in terms of x here, but we don't know what that function is in terms of x, but we know that it must depend on x because there's x involved on this side. Or if that doesn't depend on x, then the other one certainly does, and potentially that's a constant. And so then we've got v is equal to cis theta here. Okay, so when we differentiate this, we're going to get r, so that's this bit here, and then the derivative of this. Now the derivative of this, cis theta, is going to give us minus sine theta. We get minus sine theta there, and the derivative of this is going to give us plus I cos theta. Okay, and we've differentiated this with respect to x, so we really need here an extra d theta dx. So essentially what we've done is we've taken dv dx, and we split up dv and dx, and we put in this d theta d theta. So now we've differentiated with respect to theta. We didn't differentiate with respect to x. We've done this part, that's this part here, and now we need to do d theta dx. So we're just going to put that on the end. Okay, so that's essentially us applying the chain rule there. So we've got d theta dx written on the end. Now, obviously, that's only this part, so we need the other part as well. So we've got plus, and we need u dash. So that's just the derivative of this with respect to x. So that's just dr dx. That's the best we can do there. And then in brackets, we're going to have v, and v is just this thing here. So it's your cis theta, but I'll write it out fully. We've got cos theta plus I sine theta there. Okay, so essentially we've now differentiated both sides, and that's what we've got down to. Okay, so at this point we can now replace back in this thing here for e. Sorry, put that back. That's our x there. So we've now got e to the ix is still this. That's how we defined it in the first place. And I can see that that is turning up here, but without the r. But in particular, it's turning up here. Okay, so I'm going to replace this on the left-hand side. So I'm going to put in here I, and then so it's I times by this. Actually, I can do it all at once. I can say that that's I r cos theta, and then it's going to be minus r sine theta there. Okay, so obviously when we times this by I times I is going to give us minus 1. That's where we're getting this minus from. So that's just us replacing this for this thing here. Okay, and then timesing by I, and I've already done the timesing by I. And now on the right-hand side here, these two things need to be the same. So we've got on the right-hand side again, well, the whole of this. So write it all out again. I think I won't write it all out again. And so then you can compare on both sides here your real parts. Okay, so the real parts here are going to be r sine theta minus r sine theta. And on the right-hand side here, so this bit here, we've got minus r sine theta d theta minus r sine theta d theta dx, and then we have as well from this part, the real part is going to be plus cos theta dr dx, and then by comparing the imaginary parts on both sides of this equation that's coming out here, then, and obviously the derivative needs to be the same on both sides, so we could potentially create that as a triple equals here, saying these are identities. And so in comparing the imaginary sides here, you've got r cos theta here, so that's the imaginary part of this complex number here, and that's just the coefficient of I. And then on the right hand side, we can see that we've got I r cos theta d theta dx, and we also have, sorry, we don't need the I, and then we also have sine theta dr dx there as well. Okay, so now we've compared both the real and imaginary parts of both sides. Now, you can see when you're looking at these sides, you can see the solution quite simply, and I'm not going to go into too much algebra here, but you can essentially see that we have this here. If only this is equal to 1. And if this is equal to 1, then this is going to have to be equal to 0 to make this equal to 0 here, to make this whole part equal to 0 for both sides to equate. So I'm just sort of doing some trial and error here, and I'm going to put that 0 in. I'm going to see if that works on the other line. You can see, in fact, it does work on the line underneath as well. So again, this is 1 here, and this is 0 here. And again, that's working. So definitely a solution here is d theta dx is equal to 1 and dr d theta is equal to 0. Okay, now I'm struggling for space on this one. So let's just put down here dr dx is equal to 0 and d theta dx is equal to 1. Now, if you integrate both sides there, you'll see that r is equal to some constant, essentially. So integrate both sides there. And if we integrate both sides of this, we'll see that theta is equal to theta plus some other constant. Let's call that C1 and C2. Okay, so actually it turned out that r wasn't dependent on x, it was just a constant. Okay, but theta here is now, made a little mistake there, haven't I? That's equal to x when I integrate both sides, plus c2. You can see that theta is now dependent on x. Glad I saw that one in time. Okay, now the initial starting condition from this, you can see that if we put in x is equal to 0 here, we're going to get out 1 here. So e to the power of 0, anything to the power of 0 is 1. Now, to get out 1 from this, we're going to need to eliminate this part here, so the imaginary part, and we just need to end up with this part here, r cos theta. Now, to eliminate this, we could set theta equal to 0, okay, and that will get rid of this. But if we set theta equal to 0 here, so there's now no imaginary part, and then this part is going to give us cos of 0 is equal to 1. That will give us 1. So theta is 0. This gives us 1. This gives us 1 here, and therefore r has got to be equal to 1 as well. Okay, so that's a starting condition. That's definitely a combination that needs to work, that when we have theta equal to 0 and when r is equal to 1, x is equal to 0. So that's definitely a combination that needs to work with our equations. So again, let's just go through that one here. If we put in 0 here, then this disappears because sine of 0 is equal to 0. Now we've got no imaginary parts. Cos of 0 now is equal to, let's change that up, cos of 0 is now equal to 1. Now if I put 0 in for x as well here, that gives me an answer of 1 out here. So now I've got 1 is equal to 1 times by 1. And so when theta is 0, r is 1, and x is 1 as well. Sorry, x is 0, giving us 1 on the left-hand side. Perhaps it's clearer to say that when you say when x is equal to 0, theta being 0 and r being 1 is a combination which works. And that combination which works then has to also work in these formulas here. So now we can say, okay, well, r is equal to 1 gives us our constant. So now r is equal to 1. And also, theta being equal to 0, when x is equal to 0, means 0 equals to 0 there. This is 0 equals to 0, and then c2 is equal to 0 there. So in other words, theta has to be equal to x. Okay, so essentially we've now proved this thing here because we've now said that x is equal to theta, that's coming from this, and we've said that r is equal to 1. So given this starting condition, we know that we have e to the I theta there, and we also have on the right hand side here r being equal to 1. Now it would be completely fine for us now to times both sides by r, and then we get to our normal polar form for complex numbers, or our Euler's form there for complex numbers as well. Either way, both of those forms give you certainly the r at the front, when we factorize that thing out as well. It also gives us the argument of the complex number there, this position here at the top as our index number there. And you can see that that's the argument in here as well. Okay, so we've shown that Euler's formula is working. We've proved this thing here, and now instead of writing complex numbers like this, we are allowed to write complex numbers like this. All right, well, thanks for listening, guys. If you are interested, you can have a look at the other two proofs. So there's a proof using power series here. It says we're using Maclaurin series, I think. Or hang on, they're using the Taylor series there. Not sure which, but it's using power series there. And then there's another proof based on differential equations, but it doesn't give you the full working out of that one. Okay, so we've just gone through this one here. Thanks for listening, and well, good luck for the exercises if you're working on those exercises. Otherwise, hope to see you back for another video later on.